Thank you very much. I'm happy to be here. It's an honor to speak at this conference. I grew up with books of Fomin around myself in the mere translations when I was a student, so this is a big event. I would like to, I looked at speakers and I saw that a lot of people speaking about infinite dimensions, so I decided not to do it. I'm going to talk to you about something strange about control. And you know, it's the usual thing. I mean, I understand the theorems, but there are consequences that I don't understand, and they are quite shocking. And I don't know what to do about them, so there are many open questions here. So I want to talk to you about the Euler-Poincaré equations and what we call Klebsch optimal control. It's in a bunch of papers. My main collaborator is François Gebalma, but not in everything. So this is what I want to do, but I'm not going to do clearly everything. The red things are theory, the blue things are examples. I'm clearly not going to get to template matching, which is facial recognition and things of that sort. And let me make sure, okay. So let me start, I mean, it's been several days. Let me start entertaining you. Here is Poincaré's paper in 1901. This is the one that started it all off. It's 117 years ago, 18 February 1901. So here is what he says. Having the opportunity to study the motion of a hollow body whose cavity is filled with a fluid, I was led to set the equations, the general equations of motions of mechanics, in a form which I think is new and which could be of interest. This is Poincaré himself. The paper, I mean, it's Poincaré, right? I mean, it's 2 pages long. The explanation of all of this is a 37-page paper by Charles-Michel Marl. I'm exaggerating, because Marl does much more than that. So what I'm going to show you is what we call today Euler-Poincaré, which is in fact a special case what Poincaré has done. There are also the so-called Lagrange-Poincaré equation and so on. And, Professor Cruzeiro already showed you something. I'm going to stick to the simplest possible situation, exactly what Poincaré has done. And I'm not going to have advected quantities, no perturbation, nothing of that sort. But I will show you something strange very soon. So here is what Poincaré is telling you. And he really did it. It's not that it's between the lines, it's explicit. So you take a Lagrangian whose configuration space is a Lie group. You restrict it to the Lie algebra, and because one is left or right invariant depending on whether you do fluids or rigid bodies. They determine each other. Now you take a curve in the group, you take the derivative, that's a tangent vector at a point, you bring it back to the identity, either left or right, depending on what you're doing. Elasticity is on the left, fluids is on the right, for example. And then Poincaré is telling you that the following 4 things are equivalent. The first one says that G of t satisfies the Euler-Lagrange equation for L on G. The variational principle of Hamilton is true. So you take the classical variation principle. The Q's are now G. I call them G because they're in the group. These are Q and Q dots for variation with fixed points. This, you can think of it locally or globally. It doesn't matter. This Euler-Poincaré equations can be thought of as objects on the second tangent bundle with values in the cotangent bundle. I mean, think of it in any way you want. The fact that 1 is equivalent to 2 is nothing new, has nothing to do with groups. This is Hamilton and Lagrange, right? So there is nothing new here. Now comes Poincaré, and he says, these equations hold, ddt del L del xi equal to plus or minus, plus for left, minus for right, at star xi del L del xi. At xi is take the bracket with xi. It's a linear map, star is the dual map. And del L del xi is the functional derivative, so I take the Fréchet derivative and I interpret it as a vector. And the Euler-Poincaré variational principle holds, which is delta of L of psi of t dt equal to 0. Notice there is only one variable here, there are two. But there is a catch for variations, delta xi, which are the form eta dot plus or minus psi eta, where eta t is an arbitrary path that vanishes at the endpoints. Okay, so this is so simple that we can actually prove it by speaking. There is nothing to prove here. 1 equivalent to 2, it's classical mechanics. How about proving that 3 is equivalent to 4? Well, let's do it in our head. That's how easy it is. I take delta of this, I take delta L delta xi, times delta xi. I take delta xi, I put it inside. I integrate by part relative to t. No boundary terms because eta A is equal to eta B equal to 0. And I'm going to get delta L delta xi times this minus that. And I'm done. Right, by the fundamental lemma in the calculus of variations. So this is the equivalence of 3 and 4. So now let's prove that 2 and 4 are equivalent. I mean, they are, so what is the problem? I mean, L is left invariant, for example. So therefore, if I multiply here by G minus 1, here by G minus 1, nothing happens. But G minus 1, G is the identity. I'm not an idiot to write it, so I'm finished. So G minus 1 G dot is xi. So not that the variational principle is equal, not that the action is equal, the integrands are equal. I mean, this is as equal as you can get, right? So what is the content of the theorem? The content of the theorem is here. It's a constrained variational principle. So let me say it in words, and then you will recognize that this has to do with the Gauss lemma, in fact. So what am I doing? If I take a path of curves and I take variations, there is an epsilon by it. Right? The epsilon looks at the variation of the curves. Delta is the dd epsilon at epsilon equal to 0. So what am I doing? Delta xi is this. Imagine that you have an epsilon here, which is the variation of the curve, right? And now I take delta dd epsilon at epsilon equal to 0. That's delta xi. What is eta? I take dd epsilon first, and then I take ddt. These derivatives don't commute, right? Like in classical Riemannian geometry. So there is a difference between dd epsilon ddt or ddt dd epsilon, and that is given by the bracket. Of course by the bracket, because the only connection around here is Maurer-Cartan, right? So this is actually the content of the theorem, with proof. So now you say, oh, I mean, this is fantastic because I have a variational principle, so I can go to the literature on the calculus of variations. I pick up a book at random, look at the theorem, and just quote theorems. And I have a machine to do theorems, right? Not true. You know how many theorems about this are known? 0. And all continuum mechanics is like this. This is a scandal. Classical calculus of variation tells you nothing about this variational principle. It's quite interesting. So now, the question is, if you solve the Euler-Poincaré equations, have you solved the original equation? The answer is yes. It's an algorithm. This is the magic of reduction. I mean, if you are a symplectic geometer, this is obvious, more or less. So you take the first step is you restrict to the tangent space to the identity. You solve the Euler-Poincaré equations. Now, if it's integrable, and I'm going to give you examples of integrability, then you solve it because they're integrable. If they're not integrable, then you do it numerically. There is a whole industry. I'm going to tell you a few words about this, about variational integrators. And the variational integrators have to do exactly with this variational principle. So today we know how to handle this. And then you're done. You solve the linear equation with time-dependent coefficients. G dot is equal to G xi. G of 0 is z. If you're a physicist, you say these time-ordered exponentials, you're finished. As a mathematician, you cannot say that because we cannot solve the equations. We say quadratures, and we have to deal with this. And then you're finished. If the initial condition is at the base G0, right? Then you bring it to the identity. You have a Lie algebra around xi0. Then you write simply that the solution is v of t, g0, g of t, xi of t, where xi of t solves this with this initial condition, and g of t solves this with this initial condition. Done. So I have cut the problem in half. That's what reduction does for you. Right? You have some conserved quantities in general, and you are able to cut it down. Right? But in symplectic geometry, you get one more variable for free. So this is it. So this is exactly what happened here. I started with q and q dot, and here I have only, this is 2n variables, this is n variables. And I'm finished. Okay, so let's do the free rigid body. This is super classical. I mean, giving a course on this subject takes you through the whole of mathematics. So here is what's going on. You take the group to be SO3. The Lie algebra is 3 by 3 symmetric matrices. The Lie algebra isomorphism with R3 with the cross product is given by take the cross product operation. Here it is. The coadjoint action, the one with star, is also taking the cross product up to a sign. This is the sign is important. Okay? And now the energy is just the kinetic energy. So I write it in various ways. I write it as vectors. I write it as matrices, where here this operator I write it as matrices in the Lie algebra SO3. So I is diagonal I1, I2, I3. This lambda is given by circular permutations. I1 is equal to lambda 2 plus lambda 3 plus etc., the other guys. And so the kinetic energy, without Euler angles, without conjugate variables or anything, here it is. It's completely intrinsically written in this fashion. If you put Euler angles and their velocities, you will get a horrible formula, which is exactly this formula after you work in the chart. But you don't need to work in the chart. But this has a tremendous advantage because immediately you see that this is left invariant. If you replace A and A dot by BA dot, it's completely obvious that the B cancels because it's A minus 1 here and there is B, so the B's go away. So this is a left invariant energy function. Okay, so you have the free top equations. There is a Poisson bracket. I'm not going to talk about Poisson brackets anymore, or almost nothing. I'm going to stay on the Lagrangian side. Here it is. There is a sign here. It is because you do in convective coordinates, the signs are important in spite of what pure mathematicians tell you that they don't matter. They do. Because in continuum mechanics, one is convective and one is spatial. Do you work in Eulerian coordinates or do you work in body coordinates? And there are relative signs that change. So anyway, here it is. This is the orbit Poisson structure. And you write f dot equal to fk. These are my conventions. I'm a dq HDP person, as opposed to some who are dp HDQ. So you have to be careful with the signs. Okay, and you get pi dot equal to pi omega and a dot equal to a omega. What have I done? I have written for you the geodesic equations of this left invariant metric k. I take this inner product given by the mass distribution. I make it left invariant over the group. And I'm interested in the geodesic equations. Now that's a vector field on the tangent bundle of SO3. It's a Lie group. It trivializes SO3 cross R3. And what is on R3? It's this equation, and on SO3 is this equation. Clearly you see again the miracle of reduction, because a priori this vector field should split in two, and it should depend parametrically on the other variables. But on the Lie algebra, there is no dependence on the attitude matrix A. Only here you see the attitude matrix. So it's clearly how you have to solve it. You solve this equation in and by itself, then with the solution that you find here, you plug it in here and you're done. Okay, so now historically, I should tell you, this is an interesting story. Historically, it's interesting that these equations, pi dot equal to pi cross omega, were written by Euler. I'm convinced that what I'm telling you, Euler knew. He had no manifolds, no Lie groups, no nothing, but he knew it. It cannot be an accident that he wrote these equations and the fluid equations. It's the same thing, change the group. One is convective, one is spatial. That's all, that's the only difference. So, you look at this, And you say, well, is this Hamilton's equation? Nope, because it's three variables. Is it Lagrange equation? No, because it's first order. So what is it? Okay? So there were two schools. So these equations have been the first time stated as Hamilton's equations without any explanations in the book by Sudarshan and Mukunda in 75. That's how new this stuff is. Up to then, nobody understood this. And they didn't explain it. They simply said, look, if I take this and I write this, I'm going to get this. Just as an observation. So there were many people who tried to understand this. So one school in mechanics and in geometry said, we don't care. This is an accident. The representative of the school is Whittaker. You cannot find this equation in Whittaker, even though he solves the rigid body equations with theta functions and everything in great detail. He does not write these equations down. The other extreme is Hamel and Chetaev, who were obsessed by these equations and tried to understand them. If anybody would have told, if you look in Hamel's 1949 book, Theoretische Mechanik, it's a book that thick, and he really tries to understand it. If somebody would have told him, don't work with vectors, work with Lie algebra, I'm sure he would have done it. He's coming dangerously close to do it in the modern way. But he can't, because he never uses Lie algebras. So then there were other people, no lesser people than Kelly and Klein, who tried to understand it. So they introduced parameters. What they did is they have a system on C2, and they have a map. It's not a change of variables, right? Because it goes from 4 variables to 3 variables. It's a map that goes from C2 to R3. And they show that if they take this Hamiltonian, the kinetic energy, pull it back by this map to C2, then now it's no problem. I'm Hamiltonian, I have 4 variables, I write Hamilton's equations down relative to the canonical bracket on R4, and then I have a horrendously complicated expression, which I plug in, I compute it for 3 pages, and miracle, that comes out. This is an exercise I give to my students. Then they appreciate abstract theory. After you do this computation, you really sweat. Well, because this was so important, Kusterheim and Stiefel also wanted to do this, and they did it for quantum mechanics. Today for celestial mechanics. Today you see it mostly in quantum mechanics. They are not related, they are equal. They are the same thing. It was a rediscovery. And because this is so important, it was rediscovered by the topologist, and it's called the Hopf vibration. Okay? So 3 groups of people rediscovered this in completely different areas of mathematics. Today, the easiest way to say it is the standard momentum map of SU2 on C2. SU2 represents on C2, you compute the momentum map, this is what you get out. And the fact that this map from 4 variables to 3 variables gives you Hamilton's equations is nothing more than the fundamental theorem of momentum maps that tells you that the momentum map which is equivariant is automatically Poisson. Hence, Hamilton's equations go to Hamilton. Finished. So you can do the same thing for fluids, but I'm going to go very fast here. So this is essentially due to Arnold at a formal level. Then Ibn Marsden did the analysis, and then there is much more in Marsden and Weinstein. I'm going to show you a little bit more. It's standard notation for everything. But now I have a group. This is not a Lie group, unless you go to diffeologies or convenient calculus or something, and my answer is don't do it, it's not good for PDEs. So you have to stick with Sobolev classes, and in Sobolev classes this is not a Lie group. Right invariant is C infinity, left and inversion are only continuous. So you cannot use Lie group theory. However, Lie group theory is telling you what you should try to do, and what is the path you should follow. And then you prove things by hand, if you can. In this case you can. But now you have a problem, right? Because the Lie algebra is divergence with vector field tangent to the boundary. It's parallel to the boundary, right? So here it is. And now you work in, you're supposed to write things on the dual. But in infinite dimensions, the dual is in the eye of the beholder. I decide what the dual is, right? There is not a single dual. So if I decide that my dual is relative to a weak pairing, so it's a formal dual itself, which is L2, and I write the Euler-Poincaré equations down, I get the Euler equations for the velocity. Okay? It's an extremely interesting exercise to carry out and to see why and how the pressure comes from. You already know from the talk of Professor Cruzeiro, because you have a Hodge projector here. That's where it's coming from. Okay, and there is a bracket. There it is. But as a geometer, you say, I mean, this is crazy. I mean, duals of vector fields are not vector fields. They're forms. But vector fields are only divergence free. So the formal dual is one forms. If you carry this out and you are careful, you are going to discover that if the first cohomology of the manifold is 0, and I'm going to work like this to make it very easy, it is simply exact one forms, the dual. So now you want to write the equations of motion here. So you write the Euler-Poincaré equations down. And what you got is d omega dt plus L v omega equal to 0. I have just covered about 10 weeks of fluid dynamics in one slide. Okay? I have just shown you that the Euler equations are identical to the vorticity equations. And you're going to see how far I'm going to get in a moment. So, of course, this is the Lagrangian, and I tell you how to solve what are the equations. So these are the equations on the Lie algebra. Where are the equations on the group? This and this together form the geodesic equations on T of the volume-preserving diffeomorphism group. Okay? So now let's really do fluid dynamics to show you how fast it goes. So I'm going to show you that the following statements are true and they are equivalent to each other. And of course, as soon as this was done by Helmholtz, Poincaré was so impressed by it that he wrote a book. I mean, Poincaré knew what he was doing. He really did. There is a whole book dedicated to this. But here it is. The vorticity is transported by the flow. But this is a total triviality, because these are the equations of motion, and this is the Lie derivative formula. Right? So this is 0 if and only if this is 0, which is if and only if this is constant. Okay? The solutions of the vorticity equation remain on coadjoint orbits, of course, because the coadjoint action is given by pullback. Nothing to prove. Kelvin's circulation theorem holds. What does it say? For any loop C in M, bounding a surface S, the circulation remains constant. Okay, let's prove it. Here's the proof. That's how easy it is. So all you do is you look at this. You use Stokes. This is the surface. Okay? Now, this is notation. It's omega. You use the fact that this is transported by the flow. You change variables, but nothing happens with the domain. Okay? And you're finished. I mean, there's nothing more to show. I just gave you a full incompressible fluid course in 2 slides. This is the power of what you do with geometry. Let me show you another one. Here is KdV. Okay? So this has to do with the so-called Bott-Virasoro group. So I'm taking the Bott-Virasoro group is a unique non-trivial extension of the orientation-preserving diffeos on the circle by the line. So as a set, it is literally the cross product of this set with this set. Now to make my life easy, I interpret my orientation-preserving diffeo as strictly increasing diffeomorphism of R. So all psi of x plus 2 pi is psi of 2 pi, right? Okay. Now the multiplication is the following. If there would be only composition here and addition here, it would be the direct product. But it's a central extension, so it has a cocycle. This cocycle is known, and it has the name of the Bott-Thurston 2 cocycle because they discovered it. In fact, historically, it was not like that. I tell you in a moment how it was done. So here is the Bott cocycle. This is a group 2 cocycle. Just check the identity. It's true. It's far from obvious. I mean, you cannot do it in your head. The Lie algebra is, of course, as a vector space, the product of vector space of periodic functions and the line. This is the Virasoro algebra, and the bracket is, take the bracket of vector fields, and here you have a cocycle. This cocycle is the Gelfand-Fuchs cocycle. And this was known before, and this is the Gelfand-Fuchs cocycle, here it is. And what these people did, they managed to integrate it, which is a highly non-trivial affair. Okay? So that is historically how it was done. But as far as we are concerned, everything is fine. I'm going to take the L2 inner product, so on the numbers I just take the product, and I compute the coadjoint action, and here it is. The coadjoint action has a 0 here. Okay? So what is the link with fluid dynamics? Well, it's very simple. I have a Lie algebra, I have a group, I have a formula, I compute the Euler-Poincare equations. So here are the Euler-Poincare equations. There is a minus here now because I'm working on the right, because I'm in fluids, not on the left, right? So I get this equation where C dot equal to 0. This is KdV. This is our observation due to Ovsienko and Hessin. And if you change the metric to H1, you get Kamasa-Holm. Do exactly the same thing. Replace this by UW plus V prime W prime plus AB. Do this, you get Kamasa-Holm. And that's due to Misiolek. Now, you have a Lie algebra and you want to look at its orbits, right? You want to understand these orbits. So here is the picture of the orbit space of the Bott-Virasoro group. This is the moduli space. So there are hyperbolic orbits here. There are elliptic orbits at this point. This point doesn't exist, so it's disconnected. Okay? These are parabolic orbits. And this also. And the picture wants to suggest that certain things can be separated and others not. It's non-Hausdorff. These 2 points cannot be separated. These 2 points cannot be separated, but this and this can. And this repeats itself at every integer. Why is it important? The parabolic orbit 0, 1 is the Teichmüller space. It's the universal Teichmüller space. And the universal Teichmüller space is a group, but it is not a group as a quotient group. There is a whole theory. This explodes in your face. This is the whole theory of universal Teichmüller spaces. You have to understand the group structure coming from quasi-symmetric homeomorphism. This has nothing to do with this. The question is, what does it have to do with all of this? I have no idea, even though I know a lot about the Teichmüller space and its geodesics. I don't know what more I can tell you. These are questions that are open. Why is it only here? What happens at the other points? I have no idea. Nobody does. Okay, so now I'm going to show you something weird. So you can generalize to n dimensions. I mean, I'm here, just around the corner is the world expert. It's Professor Fomenko on this subject. So you can generalize it to n dimensions. Here it is. The cross product becomes a bracket in SON. Same formula, same everything. It's all identical. The pairing is -1/2 trace, because this is -1/2 trace of psi eta, if psi and eta are skew symmetric, is the dot product of the vectors with the coefficient -1/2. And of course you get exactly the same thing. These are geodesics, the Lagrangian is given by the kinetic energy, etc., etc. Question, is this integrable? And Manakov in 76 saw the following thing. He noticed that m dot equal to m omega is equivalent to these equations. This is a highly interesting statement, because look at the left-hand side. Lambda is a formal parameter. Lambda, capital lambda square are constants, have to do with moments of inertia tensor. So the left-hand side is clearly m dot. The first term on the right-hand side is clearly m omega, so I'm okay. The last term is clearly 0 because it's a bracket of lambda squared with lambda. But there is a term in lambda that must die, and it does. It's a computation. It does. So then, because this is a Lax equation, you know that the traces of the powers are conserved. But if the traces of the power are conserved along this equation, they are conserved along this equation. But you expand them as polynomials. Therefore, the coefficients have to be there, right? So the coefficients are conserved. Now you have tons of conserved quantities. So now you have to be careful. Some of these coefficients are constants, are just numbers, right? Forget them. Other coefficients happen to be traces of powers of m. Those are Casimirs, they don't count. So you have to make a careful counting, and Manakov did this, and he comes to the conclusion that he has half of the dimension of polynomials that remain after you do the correct counting. And then he poses the question, is this integrable? Immediately after he wrote the paper, there appears an announcement of Michenko and Fomenko that showed that yes, it is integrable. And then there is a huge amount of work that has been done, which is one of the most impressive works in integrable systems, because they generalize it to any semi-simple algebra and beyond. So I give you a Dynkin diagram, I can write rigid body equations, they are all integrable. There are still open questions, but I'm not going to go there. Now I'm going to show you something strange. Look at these equations. Q dot is equal to Q omega, P dot equal to P omega. I give you no motivation why they are there. Just look at them. And then regard omega as a function of Q and P. How? Via this equation. So omega is J minus 1M, so you invert this omega lambda plus lambda omega, which you can, right? And M is given by Q transpose P minus P transpose Q. Okay? A completely stupid computation says that if you take M dot, you are going to discover M omega, where omega is J minus 1M. What has just happened? I mean, I gave you a beautiful theory before, and now I'm telling you it's coming from the sky, something completely different. There is much more. I mean, the proof is literally that much. It's half a line, okay? But it's getting better. The spatial angular momentum, which is the momentum of the cotangent lift reduction, if you know your symplectic geometry, equals PQ transpose minus QP transpose. That's quite something. And that is true for the rigid body. This is how you describe the motion. It's a super integrable systems. In addition to that, it's actually even better. Individually, these are conserved. I mean, there's clearly something very good going on. What? So there is a way to solve it. I'm not going to, I don't have much time. I'm going to skip it. You can solve the equations from one to the other. And there is a Hamiltonian structure. You take GLN cross GLN, which is just a vector space finite dimension, and this dual. Of course, it has dq HDP. You write the symplectic form. Here it is. And then you discover that SOM cross SOM, in fact, is a manifold, is a submanifold of this manifold, which is symplectic. Now you want to write a bracket. How do you write a bracket? Using the Dirac theory of constraints. There is a formula of Dirac, and you compute the Dirac formula, and it's complicated. Here it is. This is a Poisson bracket. You want to give some student really hard time, tell him to check Jacobi. Good luck. Okay, but it's true. So you take the Hamiltonian, which is this, and look, on SOM cross SOM, this is invariant. Okay, this is wonderful. So it's working as it should be. So now I'm going to completely switch gears. Completely. Forget mechanics. Completely. Just stop. I'm going to do control. Just because I have this inspiration. So I take a time, I take an initial point and an end point in SOM. Here is my cost functional. I give you a constraint, which is just Q dot equal to QU. And then I can check. And literally, it's not more than this. You just compute this. That the rigid body optimal control problem, call it like this, has evolution equations Q dot QU and P dot equal to PU. What is the P? It's the costate vector coming from the Pontryagin maximum principle. Here it is. Right? So clearly something much more serious is going on. So we can look at control problems at this point. So I'm going to give you some Mickey Mouse version of control theory, because if you really want the Pontryagin maximum principle with all details, it takes over 2 pages to write, with all the correct function spaces, how many derivatives, etc., etc. Let's do it formally. So I give you a manifold, I give you a vector space, I give you a cost function, I give you a smooth function Q cross U in TQ, which is really a parameter-dependent family of vector fields. So at every U frozen, it's a vector field on Q. I give you an initial point and an end point, and the optimal control problem asks, find curves Q of t and U of t that minimize the cost subject to a given dynamics, start here and end here, right? I mean, this is military stuff, right? I mean, an airplane. I mean, this is it's not a joke. That's how it was invented, right? I have so much fuel. I have to minimize it. I have to go here and bomb here, right? And there are physical laws that restrict me. I cannot do anything I want, and this is the dynamic. This is given to me. The physical laws. Okay? So Pontryagin comes along and says, look, we cannot quite solve it, but we are coming very close. Consider, pretend in your mind that this G also would depend on Q dot. But it doesn't. But just, okay? What would you normally do? You would use the Legendre transformation. That's exactly what he did. P Q dot minus L. There it is. Right? So, the Q dot must be X. This is my P that I have to, the new variable, right? And this is my Lagrangian, but of course I cannot say Lagrangian because there is no Q dot. But formally it's like this. And P0 is a fixed positive constant. And now the theorem in its simplest possible formal way is the following. It's a remarkable theorem. It says that if Qt and ut is a solution of this optimal control problem, then there must be a curve in the cotangent bundle such that this curve is a solution of a Hamiltonian system. Which Hamiltonian system? The one I just gave you before, except I have to be a bit careful. So first of all, you see here there is an index u of t. So whenever I write hu of alpha, it means that I have a parameter-dependent family of vector fields. This Hamiltonian is time-dependent, but not explicitly time-dependent. It depends implicitly on time according to u. How do you compute u of t? You compute u of t by maximizing the Hamiltonian on alpha t and u. It's all implicit, right? I cannot do this and then do this. It's all implicit. That's part of the problem, right? But this is the answer. If P0 is not 0, do you replace alpha t by this over P0? Then you can always assume P0 is 1. These are called normal extremals. If it's 0, they are called abnormal extremals in the whole theory of it. I'm not going to go there. Let's cut down the problem more and more and more. I'm going to take H to be C1. Well, this is maximum. I'm going to solve it by solving the H du equal to 0. Now, sufficient conditions for maximum to exist along the control u of t is that X is linear and G is strictly convex. These are theorems in control theory. And in addition, the optimal control is unique. So locally, the Pontryagin maximum principle states that if alpha t is qt, p of t, and ut are determined, then these are determined by this system. Here are Hamilton's equations, and I already know half of it is that it's exactly the dynamics that I have given you, and the h du must be 0. Okay, assume that I can solve it. I can actually solve u as a function of alpha. Now I have h hat of alpha. Now it's a function of alpha. It's an honest to God Hamiltonian, not time dependent. Everything is wonderful. And then, sure enough, there is a variational principle that gives these equations. Okay? So let's do an example. A very, very simple example. The simplest example is this Clebsch optimal control problem. I give you an action of a group, and this is my notation for the infinitesimal generator, and the Clebsch optimal control problem tells me, I give you a function, I think of it as a Lagrangian, I give you a function, here, L u of t, q of t, this is my cost function, and my dynamic is determined by the group action. So I want to explain this notation, so here is what you do. At any given time t, you compute u of t. This is a Lie algebra element. Take its infinitesimal generator. That's a vector field. Evaluate it at q of t, the same time t. It's necessary to put a t here, and it's necessary to put t here, and it's necessary that they're equal. The same time t. And in the inverse problem, you do it the other way. One is left versus right. And then you put initial and condition. So this is a particular case. My vector space is G. My cost function is my Lagrangian. My dynamics is given by the infinitesimal generator. So I'm already linear in U. The Pontryagin function, in this case, I can give. And now comes the first shock. This is the momentum map. I never asked for it. It's there. Okay? All right. Can we solve the problem? Yes, we can solve the problem, actually. So the solution that the theorem says that the extremal solution of the Clebsch optimal control problem satisfies this delta L delta U is J alpha. Alpha dot is equal to this. This is the infinitesimal generator on T star Q of the lifted action. The colors I'll tell you in a moment. This implies the Euler-Poincaré equation for the control U. Here they are. If L does not depend on Q, the brown terms are gone, and I have the Euler-Poincaré equations. But I never asked for it. I was not doing a mechanical problem, I was doing control. I have solved the problem completely. I solve this equation for U, then I write G dot equal to G times U, linear equation with time-dependent coefficients. I solve for G, and then I write alpha equal to the lifted action of alpha 0. Theorems guarantees to me that this is equal to that, which incidentally is Hamiltonian, and that this is true. Problem solved. I solve the control problem by mechanical considerations. If a serious control theorist would not be very happy, this is a fully actuated problem. I grant you this. It's not one of the hard ones. That's true. So there is a variational principle going with it. I can write the Hamiltonian version of it. You start discovering symplectic geometry right and left, where you didn't even want it. I'm not going to give you the proof, but I want to show you this and then I stop. Let's take the kinetic energy cost function. Right? Kinetic energy cost function, if I take L of U equal to this, the Pontryagin function is norm square of the momentum map. I mean, if anybody has done anything in symplectic geometry, this is a big warning sign. This function is crucial. The Morse theory of this function gives you the convexity theorem for the momentum map. Are the convexity theorems for the momentum map much more general? Are they a control theoretic phenomenon? I have no idea. I have absolutely no idea. But it's a very good question. I have gotten into deep symplectic geometry by taking the simplest possible example. And of course, if I would continue, I can show you that this rigid body situation that I did before is one of the very special cases of what I just explained to you. Thank you.
Okay, some questions? No. Okay, so
We go to lunch.